So let's talk about the full definitions. Let's talk about instantaneous velocity and speed. So that's just our derivative. So here, we can talk about changing velocity. So let's say we go 3 different speeds, just like this guy did. So if you want to plot this from here to here, right, to 200 meters, we're going at 1 speed. Then we go slower for a little while, and then we speed up. Okay? However, each section of these is the same average velocity, but you now have 3 different velocities. Okay? So this is a changing velocity, kind of. It's more of a piecewise change, to use a math word that just means chunks of a graph. Okay? And so, you know, these are, so I don't know why they did that, but if you want to graph this, how would it look? Well, like ramps, yeah, but little stairs, yeah. So the first part looks like this, then the second part looks like this. We use the same method we did before, and we basically get this part, and this part. So 3 lines, 3 straight lines, but they're all slightly different, okay? It's medium speed, slow, and fast speed. So this would be medium, slow, and fast speed. So how many slopes do you need to find? 3. So if you want to actually draw the position graph, the velocity graph, you start with this one, you'd figure out the slope, and then you plot it over the same time. Okay? Then you do this one, you figure out the slope, you plot it over the same time. This one, figure out the slope, plot it over the same time. But remember, we want our velocity graph to be green. Why are these lines dotted? You can't instantly go from this speed to this speed. In real life, there'd be some like curvature here to transition from one to the other, but since we're just doing this simple part, we're going to ignore that for now and just say, this is suddenly we're going this speed. Okay? Okay. So let's practice that. Let's do a problem where you take this graph, right, and you want to draw the velocity versus time graph. Okay? So we'll take about 5 minutes, draw the velocity versus time graph for this position graph, and then we'll move on to the next thing. Okay, in the interest of time, we will go over this. So the first thing we want to do is figure out what the slopes are for each thing. So we'll start with, let's say this section. So from 0 to 2 seconds, what's the slope here? Yeah, so this is going to be -2 meters per second, right? Because the rise is from 0 to -4, so from here to here, and your run is 2 seconds. So -4 divided by 2, that's -2 meters per second. Everybody cool with that? Yeah. Okay. How about the slope for this part? That would be 0 meters per second because it's just a horizontal line. Okay. What about the slope for this part? That's going to be 5, that's 10, a rise of 10 divided by 2 seconds. So this is going to be 5 meters per second. So we're going to take that and we're going to try to draw our velocity versus time graph, which we're going to represent like this. So here's velocity over time, and we're going to have the same units. So this is going to be 1, 2, 3, 4, 5, 6. That's not great. I should have done that better. This is the fun thing about drawing graphs. So 1, 2, 3, 4, 5, 6. Okay, approximately right. And we're drawing the time because the time's still going to matter. That's in seconds. But now this is going to be velocity in meters per second. Okay? So what do we do for the first part from 0 to 2 seconds? It's a straight line because remember it's a constant velocity and it should be at -2. Okay? So we're going to draw a straight line at -2 from 0 to 2 meters per second. 0 to 2 seconds. What about the second part? It's 0. The velocity is 0. So from 2 to how many seconds? 4 seconds. We're going to be at 0. And then last but not least, what do we do for 4 to 6 seconds? We should be up somewhere like here at 5. So we have a straight line at 5. Now, there's a couple things to note here. One, this is going to be 5. This is going to be -2, so you could write in 1, 2, etc. 1, 2, 3, 4, 5, whatever. 1, 2, 3, 4, 5. We also want to connect these with sort of these dotted lines, so you get the idea that there is a transition. We're just not really representing it. And then if we want it to be really fancy, we could say, oh, we always want to represent this with green, so we're going to do it like this. Okay, that was a terrible green. I don't think you can see it, but whatever, you get the idea. But, you know, the transitions we're ignoring because obviously there's some acceleration that has to happen to change these velocities. But the key is if we have constant velocity, that means it's a straight line slope here. And when we have the constant velocity, it's represented as a flat line on the graph. Okay? Everybody good with this? Cool. Let's go back. Okay? So let's say we actually just speed up continuously. So instead of just changing speeds, we go from velocity. Wait, did I skip something? Hang on. I think I missed something. No, I guess I didn't. All right, so let's say we want to go, let's say we want to go backwards. All right, I'm getting ahead of myself. Let's say we want to go backwards. Let's say we know the velocity and we want the position. What do? We're going to integrate. So what that means is to figure out what's happening at 1 second, we take the area under the curve from 0 to 1 second, okay? What's that area going to be? 12. So we plot that at 12, okay? Then from 0 to 2 seconds, okay, that's going to be 24. So we plot it at 24. From 0 to 3 seconds, et cetera, et cetera. Now you have this going the other way, okay? If you want to do this in a full math way, you want to write it like this. And this is a fun thing we do in physics that mathematicians don't really like, where we're essentially saying, if you want to call this, here's a little side math for you. So if velocity is dx dt, okay, we do this thing where we say, let's multiply both sides by dt. So we have v dt is equal to dx. And then we integrate both sides. You end up with delta x, because this is x initial to x final, is going to be equal to, let's see, vt plus c, which you get from this. So you can just call this either x to x initial, or delta x is equal to vt. Okay. The integration part depends on the formula, so you can get slightly different things. But what we're doing is basically splitting up the derivative and using algebra on it. Okay? Here's a clicker question. Okay. All right, we're a little over the place, but most people think B. Please discuss. We'll vote again.
So it was going forward.
Okay. You've discussed and you feel like you have a good answer. Please vote again. We lost one person. Ooh, nice. B. Cool. The answer is B. Thank you, people in the chat. I can see you've all answered B as well. So maybe I'll just get clickers for the people in the Zoom chat and just like add them to the thing. Cool. So this is the correct answer. What do we know about the number of speeds we see here?
It changes once.
2. We have to have 2 different speeds. So how many of these have 2 different speeds? Only this one, right? Like, what would the graph of velocity be for this?
0.
0, right? What would the graph of velocity be for this?
0.
0. So there'd just be a flat line. This one would have this part, but nothing else. So that's what all of those would look like as velocity graphs, okay? Good. I think we're getting the hang of this. So let's say we have changing velocity where we just actually speed up, okay? So that would look something like this. So each of these snapshots would be a different velocity vector. So we have a constantly changing velocity. And what does this look like when you plot it? Well, if you just do the method we used before, it looks something like this. What shape is this graph? It's a parabola, right? So, which if you're talking about Excel or like sheets, they call that power. Just FYI when we start graphing things in lab, but it's something squared, right? So that makes sense because the slope, right, at y equals mx plus b, this is linear, okay? What happens if you integrate x? What do you get if you integrate x? Oh, no, sorry. What happens if you integrate t in this case? Like just to the variable. We can call it z if that helps.
It raises a power.
It raises a power. So you expect if you had something linear, like if you take a derivative of this, you'll get something linear. If you take a derivative of that, you'll get something flat. Okay, so we've only been doing linear to flat. If you take a derivative of something that looks like this, your derivative looks like this. If you want to get a derivative that looks like this, you need something that's shaped like this. And I know exponential and power, when you're not dealing with physical stuff, seem pretty similar looking because they're both curvy. But there's a big difference because exponential is like a much more extreme version of sloping up. It only really comes up when we talk about exponential decay and like radioactivity. It comes up in like population dynamics, and it comes up in electronics when we talk about charging and discharging capacitors. But other than that, it doesn't come up too much. Usually we're doing powers, okay, because the changes are much more gradual. And so here we have our this line, right? This now our position graph is parabolic, or power of 2, okay? It's not straight at all. How do we find the slope of this line? We just take a derivative, right? This is almost the definition of calculus. I almost feel stupid for making this slide, but you're just taking the slope at each point. So here's what a derivative is. You take the slope at this point, and then you make the intervals smaller and smaller until they're infinitesimally small, and then you're just taking the slope at a point. Okay, so now that we've defined what calculus is, it's the instantaneous velocity at each point. So if you wanted to figure out the velocity here, you figure out the slope at this point, which is the tangent, right? Slope at this point gives you velocity. You can see the velocity here is much less steep than the velocity here, so we have changing velocity, okay? So if you actually wanted to plot that, it looks something like this, okay? So we have this other line with a slope. What does this one mean? Well, that means we have a velocity that changes over time, okay? So our position is changing over time too, but it's changing really rapidly, and the change changes with time, okay? That's what second derivative sounds like if you try to say it in English. Then you have a velocity that's changing in time, so that means you're not going the same speed here as you are here, okay? So you estimate this with instantaneous. So here's just a sort of a general way of thinking about this in calculus. So let's say we have a position, and it's given by this equation. Okay, how do we plot that? Well, let's see, it looks something like this. Okay, this is it's weird. You'll see this 0 is here, so we could have put a line here, but just for the sake of things, it's so we can see it better, it's plotted like this. Okay, if you want the velocity, you take the derivative of this. So this is negative 3t squared plus t. Negative 3t squared, oh sorry, plus 3. Okay? So if you wanted to plot that, that looks like this. Okay? So all this calculus we've been doing is actually physics, and we end up with something that looks like this. So if you want to look for the different inflection points, they all mean something. Okay? What's the slope here? 0, right? What does that tell you is happening there? You are changing direction. Okay, that is a slope of 0, which means, look, you're changing direction. What's your velocity there? 0. And that's what we mean by an instantaneous velocity of 0, right? This thing is moving the whole time, but just at this point, it has to stop to turn around. Okay? So what's the particle's position at 2 seconds? How do you find that?
You just plug in 2 into the top equation.
Yeah, you just plug 2 into the position equation, right? For time. So you can do that, and you plug it in, and you get negative 2 meters. Okay? If you want to figure out the particle's velocity at 2 seconds, you plug it into the velocity equation. Okay? So this is just saying all this calculus we've done in math has applications in physics, specifically in kinematics. Okay? I think we have a couple more seconds. So we'll do this last slide. So let's try this out. Mostly thinking C. Please discuss, and we'll vote again. We're mostly thinking C. So what's going on here? What's going on in this segment of the... Oh, that thing's not following me anymore. In this segment of the graph. So pretty much a constant velocity, which means that you're looking for something flat, right? And then the second part, you're going from something that's moving slow, like it's changing quickly to changing slowly because it flattens out. So right at the end, what's your velocity? 0. So you're looking for something that is flat and then changes and then is 0. So these two are your best options, but because this is a positive slope, this one is better than this one. So C is the correct answer. Cool. So if you want to go from velocity back to position, right? Let's say you know what your velocity graph looks like and you're trying to figure out what your displacement or position is at a particular point. What do you think you should do? Integrate, okay? If you're going from position to velocity, you take a time derivative of your position versus time function or graph or situation. If you want to go the other way, you take an integral, okay? Now, that doesn't necessarily mean you're doing all this integration that you learned in calculus. What is the visual meaning of an integral? It's the area under the curve. So a lot of times you'll notice these graphs look like rectangles and triangles. Is it easy to find the area of a rectangle?
Yeah.
What about a triangle?
Yep.
What about a rectangle next to a triangle, which sometimes we call a trapezoid? Yeah. And even if it's kind of round, you could probably estimate the area under the curve, even if you can't figure out how to do like the technical aspects of taking an integral, okay? So the only real, so this is basically this is the definition of an integral. The book tries to sell it to you like they're teaching you calculus from scratch, but let's just say it's an integral. It looks like this, okay? Now the main difference here is in order to actually plot the graph with the positions, what do you not have that you need to know if you just have a graph? The plus C. Whenever you do these indefinite integrals and you get plus C, that's something in later in math they call the initial conditions. So you need to know where you started. So if you don't know where you started, you can get the shape of the graph, but you don't know how to write where it is in space. Okay? So, for instance, if you have a line, you know you're going 1 meter per second, right? You can write that your position graph is going to have a slope of 1, but you don't know whether it started at 1, at 5, at 0. It's always going to have the same slope, but your y equals mx plus b, the b is going to change. Okay, that would be the initial condition. So if you know it starts at 0, then you have a graph that starts at 0 and is linear with a slope of 1. you know it starts at 1, you just shift the whole graph up. So you always have to be looking out for words when you're going from velocity to position that tell you where you started. Okay? All right. Here's a question. Oh, and a lot of us do. Okay. So please discuss. We'll vote again. Remember the difference between displacement and position. Okay, better. E, interesting. So, if we want to figure out the displacement, when are the times we're worried about?
0 to 10.
0 to 10. Okay? And so to find displacement, we don't actually need the initial conditions because displacement is just the change in your position. Okay? So that we can do without any initial conditions. So from here to here, we have to take an integral. Now you can, although there's no real, it would take longer to write out the equations for this part of the graph plus this part of the graph and then actually integrate it. You can do that, okay? And then you would integrate, you'd write an equation for this, integrate it from 0 to 4, then write an equation for this, integrate it from 4 to 10, and that would work. But since we all know what a triangle is, hopefully, okay, what we want to do is just figure out the total area. Now you'll notice this area, is this positive or negative?
Positive.
Positive. What do we do with this area?
Negative.
It's negative because the line drops below the axis. And so here you have to figure out the area of this triangle. So that would be 1/2 base times height. What's the base? 8. What's the height? 4. So 1/2, 8 times 4, 16. Okay, so we start with 16. All right? Then you subtract off 1/2, -2. Well, so 2 because we're already using subtraction. So 1/2, 2 times 2. What's that?
2.
So we have 16 plus -2. Okay, what's 16 minus 2? 14. So the answer is going to be 14 meters. Now, what does this actually look like if you're trying to do it? Let's say this is a person walking. Okay? So let's say I start here. All right? What does this velocity graph tell me I'm doing? You're speeding up. Okay, and then I slow, and whoops, okay, I have to start. So you start going slow, you speed up, and then you slow back down, and then you turn around. And you speed up, but you turn around. Okay? And so what that says is, as you're speeding up and slowing down for this first part, you go faster and slower, but the total distance you covered is 16 meters. And then as you speed up going backwards, you're losing 2 meters. You end up back at 14 total displacement. Okay? So remember, when you're doing this, think about what the graph actually means. The difference between physics and math is in physics, you should be able to do it in the real world. Okay? You can invent math that can't exist in reality. Physics, especially in this class, has to be fairly accessible in reality. Okay? All right. Cool. Let's try this one. This is a different question. One of the words is different. So we're mostly thinking A. Please. Well, we have almost unanimous, just one person is an asshole. Okay, so the answer is going to be 18 meters because that's the total amount you walked regardless of where you land on the number line, okay? So feeling pretty good about that. And then when does the object turn around? Although, since I acted it out, I guess this will be great. Okay, we're mostly thinking B. Please discuss, we'll vote again. Better. Okay, so how do we know at what speed do things turn around? 0. Okay, so you have if B is 0, if the velocity is 0, that means you're either stopped or you're turning around. So that would be at 8 seconds. Okay. All right. We're gonna do a problem. It's a graph. So this is a position versus time graph of an elevator. Okay? And so it's got 3 parts. We want to figure out where does the elevator have the least speed, or does the elevator have the most speed? And when we talk about speed, we're not talking about direction. So anytime you have a large positive or negative number, that's a large speed, okay? And then we want to sketch an approximate velocity versus time graph for the elevator, okay? So let's start with the first two parts, because those are pretty straightforward. So at which points does the elevator have the least speed? A and C. What happens at A and C?
0.
Yeah, we know these things should be 0 at A. At A it's 0, and at C it's 0. Okay? Where is the speed the biggest? At B. B is your maximum speed. Okay? Why is B your maximum speed? That is your steepest slope. You can see you're going from a shallower slope to a steeper slope, and then back from the steep slope to a shallower slope, because you have to go from 0 back to 0. So B is your fastest point, which means on this graph, B will be your maximum. Okay, so we know A is here, B is here, C is here. Then it gets a little bit more subtle when you actually have to draw the graph. Okay, so let's start with the easiest part. Which is the easiest part?
The middle.
The middle?
It's just the
Where is velocity 0? C and around C, right? So we could draw all around C. We know we have 0 velocity because you can see that line's flat right before C and right after C. Okay? Then it gets a little bit trickier. You know nothing's going to go above here. Now we have to look at the slopes. So you start out with a steep negative slope. When you have a negative slope, where do you end up on here? Negative. Okay, so it starts out steep and then it gets smaller. So that means you want to start out with a large negative value and go back to this 0. Okay, so you can see steeper slopes, shallower slopes. So large negative values, smaller negative values, 0. Okay? After 0, what's the slope over here? It's positive, but it starts out shallow and it gets steeper until you get to B. So there's a couple ways you could do this, but it looks like since it's pretty smooth, it's not a good. I'm going to try to connect these dots. Okay. It's pretty much a straight line until you get to B. B is your maximum speed. Then it goes from steeper to shallower, which means larger positive velocity to smaller positive velocity. Now, if you decided that there was a flat top at B, that's okay too. You could draw it so that it like levels out right here and is flat. That works fine because this is just an estimate. Okay, so that would be appropriate. But pretty much anything besides that, you could give it a little curve. There's some leeway. But the main thing is you want to start out negative, go to 0, go up positive till you get to B, which is definitely your maximum, so nothing should be higher than B. Then you know it slows back down till it gets to 0 at C. So if you made this like a little bit curvier, or if you made it flat at the top, those are all reasonable things that you could assume, but we always want to try to make, if we're estimating, we try to make it as simple as possible. And it's really easy to draw straight lines, well, for some people. Yes?
Is the slope kind of positive after B? Slightly positive.
Yeah, it's still positive. So positive just means that you're above 0 when you go to the velocity graph. Okay? So even though it's still going up here on the position graph, you can see the slope doesn't get steeper because it doesn't turn this way. So this maximum point comes from it being the maximum slope, the largest positive slope. So even though this is still technically going up, you can see it's tapering off that way, it's curving that way, which means the slope at each individual point is getting shallower, which means your velocity is getting smaller. Okay, so it's still positive. Everywhere from A to here is positive, but it's changing the values of your positive number as the slope changes. Okay? Any more questions? Yes?
Let's say in the position versus time graph, from 0 to A, the slope was, let's say it would be like positive. How would that change the velocity of the time graph?
So like if this like came up from here, then you would start here and go up like that and come back down. Okay. So it looks something like this. If you want to like break it down, right, you can see this is how it looks, right? These yellow points are where we have zero slope. All of this green stuff is represented here. The changing slope tells you go up and then down. B is the maximum. Negative slope goes over here. Okay. All right. We're feeling pretty good about this. Do we want to try another problem with numbers? Okay. So let's try this one out. So, there's, as I've seen around the room, there are several ways to approach this problem, but the basic concept should be that we're looking for the displacement in the first 3 seconds. So we want to go from here to here and take an integral. So whether you set up the equation of the line, and what would the equation of the line be?
4x.
4t, right? Because y is x and x is t. But 4t, all right, integrated from 0 to 3 should give you 18. Or, if you don't want to do that, you can say from 0 to 3, that's the base of your triangle. Height of your triangle is 12. So 3 times 12 is 36, but it's 1/2 base times height, so half of that is 18. So both of those things are correct. They should give you the same answer. Done and done. Okay? And so as long as you know displacement is given by the integral, and the integral is the area under the curve, you should come to the same conclusion, which is that this car has gone 18 meters in the first 3 seconds. Okay? What if I asked you, so what if I said the car started at 2 meters? What position is it at in 3 seconds later?
That's just a constant integration, so you would solve for it and then add the plus 8, which would be 18 plus
So 18 is the displacement. If our initial position was 2, what do we do with those two numbers? Add them together. So that would be, you would be at position 20, because you would start at 2, move 18, now you're at 20. Okay? So that's the difference between position and displacement. Displacement is just the difference between where you were here and here. Position is your place in space based on your coordinate system. Okay? The displacement's always going to be the same, but if we change the initial conditions, if we change where we start, the end position is going to be different. So let's say we start 5 meters behind the starting line. What would your position be after 3 seconds? 13, right? Because you're going to start at -5 and add 18. So that's where initial conditions come in. What if I wanted to know the displacement between 2 and 3 seconds? What do you do then?
This 10.
So you would find the area of this thing, right? So you can either figure out the area of the trapezoid here. You can once again set up the equation and change the limits of integration from 2 to 3, or you can take this triangle and subtract this triangle because you're like, I don't remember what a trapezoid is. So, okay. So we talked about how to go from position versus time to velocity versus time, right? And how to go from velocity versus time back to position versus time. So if you go this way, you're taking a derivative. If you go that way, you're taking an integral, okay? So when you take the slope, when you take a derivative of this, it has a physical significance, okay? We know when you take a derivative of position versus time, you get what? Velocity, right? Or velocity versus time. So what happens when you take the slope of your velocity graph? When you take a derivative of your velocity graph? Yeah. Now we're talking about acceleration. So you can get average acceleration. If it's nice and linear like this, you can get average acceleration, which is now the same as instantaneous acceleration, by just taking the slope. But in general, if you take the derivative of your velocity versus time graph, you get acceleration versus time.